So previously, when proving that the set split F determines the splitting field of F, we have used the weak tributary theorem. Remember, it allows us to relate the density of this set of split F with the degree of the splitting field of F over Q. So now let's discuss a bit more about these density theorems. As we've mentioned, for a billion polynomial, i.e. polynomial with a billion Galois group, we can actually describe split F in terms of a congruence condition. But that's only if the polynomial is a billion. In the case of a non-abelian polynomial, the most that we can say is about the density of split F, which we just mentioned. Now this theorem turns out to be a generalization of Dirichlet's theorem on primes in arithmetic progression. Remember, this theorem says that if A is relatively prime to M, then the density of the set of primes congruent to A mod M is just gonna be equal to 1 over the Euler phi function evaluated at M. In particular, there must be infinitely many primes congruent to A mod M. Now, so how is this a consequence of weak tributary theorem? For this, we need to remember our discussion about splitting of the cyclotomic polynomial. Remember that the 8th cyclotomic polynomial splits mod p if and only if p is congruent to 1 mod a. So now, if we let this f be the mth cyclotomic polynomial, then split f is just going to be the set of primes congruent to 1 mod m, and the splitting field of f over q is just going to be the m cyclotomic field. So this extension is just going to have degree phi m. And thus in this case, what the weak tributary tells us is that the density of the set of prime congruent to 1 mod m is just going to be equal to 1 over phi of m. Now actually we can generalize this weak tributary theorem a bit further, and what we'll get is the strong tributary theorem, i.e. the tributary density theorem. Roughly speaking, this is gonna give us the size of the fiber of the Artin map. So what is an Artin map? So what will happen is that in the next video, we're gonna define this so-called Artin map. This map will associate to most rational prime p some element in the Galois group of F. Then what the tributary density theorem says is that if we fix a conjugacy class in this Galois group, then the density of the preimage of this conjugacy class under this Artin map is gonna be given by the quotient of the size of the conjugacy class over the size of the Galois group of F. Now, observe that when this Galois group is a billion, then each conjugacy class just consists of a single element, and thus this preimage here is just a fiber over a single element. So what we'll have is that the size of every fiber is just going to be equal to 1 over the size of the Galois group. And this could be related to split F in the following way. So split F turns out to just be one of the fiber. Actually, it's going to be the kernel of the Artin map up to finitely many exception, right? And thus, we will have that the density of split F is just gonna be equal to 1 over the size of the Galois group, which is just 1 over the degree of this extension. And that's just the content of the weak tributary theorem. Moreover, from the fact that the size of every fiber is non-zero, we immediately have that this Artin map must be surjective. This is part of the content of Artin reciprocity. So in the next video, we're gonna discuss what this Artin map is, and then we'll discuss Artin reciprocity, and then we'll show that split F is just gonna be, roughly speaking, the kernel of the Artin map. This will then allow us to finish the proof of the abelian polynomial theorem. We will be able to show that if F is an abelian polynomial, then split F can be given by a congruence condition. So see you in the next episode.